Hello, this is Neil Polhemus. I'd like to welcome you all to this month's webinar titled, Would You Have Survived the Sinking of the Titanic? This is the first in a series of webinars where we'll be looking at some real data sets. Some, like today's data, will be publicly available data sets from the internet. Others will be data that our clients have successfully analyzed with Statgraphics. What we'll be talking about in these webinars is how Statgraphics can be used to get the most information possible out of those data sets. Today we're going to be looking at some data on who survived the sinking of the Titanic. We'll be looking at survival probabilities based on things like age, sex, class of accommodation, and so forth. It's going to involve the use of Statgraphics Mosaic charts, the multiple correspondence analysis procedure, and also the logistic regression procedures. I'd like to welcome everyone to today's webinar entitled, Would You Have Survived the Sinking of the Titanic? It's the first of a series of webinars that we'll be doing here at StatPoint, looking at actual data sets. Some of the data sets will come from the internet. There's an awful lot of data you can find publicly available on the internet. Other data sets we'll be looking at are actual data sets that our clients have analyzed. And in fact, on some of the webinars, the clients will be helping us do the analysis of the data. Today, though, we're going to be looking at some data that I found on the internet describing characteristics of the passengers and crew of the Titanic and whether or not they survived the sinking. It's very interesting. You can see quite interesting relationships between the chance of surviving and various characteristics of the people on board. We're going to be using the Statgraphics Mosaic charts. We'll be talking about a multiple correspondence analysis and looking at the logistic regression procedures. The logistic regression procedure is a great way to build a predictive model. And although I really don't need to predict who's going to survive the sinking of the Titanic because that happened 100 years ago, the same logistic regression procedures are quite useful if, for example, you're a bank giving out mortgages and trying to determine the probability that a client might default on the mortgage. We just did a trade show in Washington, D.C. called Predictive Analytics World, and there's a lot of interest these days in using procedures such as logistic regressions to do prediction. Now, when they initially built the Titanic, it was supposed to be unsinkable. However, on April 14th, 1912, the Titanic struck an iceberg in the North Atlantic. And by the next morning, the boat was on the bottom of the ocean. The Titanic carried over 2,000 passengers and crew, many of whom did not survive. What makes the data set interesting for us to look at are certain controversies that have arisen. And if you've read about the Titanic or perhaps saw the movie, you'll know that there were not enough lifeboats on board to save everyone, and that individuals were treated differently depending upon whether they had first-class accommodation, second-class accommodation, or third-class accommodation. And that differential treatment you'll see quite clearly when we start looking at the data. Now, there are two sample data files that I found on the internet having to do with surviving the sinking of the Titanic. The first comes from the Statistical Archives of the American Statistical Association, put together by Professor Dawson at St. Mary's University. It contains 2,201 rows, one observation for each person that was on board the Titanic. In that file, you'll find 4 variables. You'll find a variable called class, which is coded 1 for first class, 2 for second class, 3 for third class, and 0 for crew. There's a column called age, which is a 1 if the individual was an adult and a 0 if it was a child. Sex, 1 for male or 0 for female, and survived, either a 1 if the person survived or a 0 otherwise. This is the file we're going to use when we do our cross tabulations and when we do our multiple correspondence analysis. The advantage of this file is that all the factors are categorical, which allows us to look at the counts of joint classifications of those variables. There's a second data file put together from some folks down at the University of Virginia that does a little bit more detailed breakdown, but only for the passengers. This data file has 1,309 observations. It has a column for class, it has a column for survived, it has a column for sex, and a column for age, like the first file. One difference here, though, is that the age is quantitative. It's actually years of age versus simply a 1 or a 0. That's going to be quite handy in doing a logistic regression, because we can then fit linear and nonlinear models with respect to the age variable. There's other information in this data file too that I'm not going to use, but there are columns listing the number of siblings each passenger had, the number of parents who were on board, how much they paid for their ticket, and so forth. We'll just be isolating, though, on those 4 factors. Now, the first thing I'd like to do with this particular data set is what I do with any new data set, and that is graph it. Graph it in a way that lets you see a lot of what the data has to say. And to do that, I'm going to move now to Statgraphics, running version 17 here, where I've loaded into the data sheet this data file with approximately 2,300 observations. The first graph I'm going to create I'll do by going to Describe, Categorical Data, Cross Tabulation. I'll pick 2 columns, in this case age and survived, and press OK. The default tables and graphs are fine, so I'll go ahead and look at the output of the tabulation for age by probability of survival. Now, of interest to me are the table and the graph in the bottom section of this window. In particular, there's a frequency table here which will tell me for adults and children how many were on board, how many survived, and how many did not survive. Of the passengers, 2,000, actually passengers and crew, 2,092 were adults. Of those, 654 survived. Of the children, there were 109 on board, 57 survived. Now, to see this graphically, the chart I like to look at is the Mosaic chart. A Mosaic chart will display bars for each combination of the categories. There'll be bars for adults who did not survive, adults who did survive, children who did not survive, children who did survive. the height of the bars are proportional to the breakdown, percentage breakdown on board the Titanic between children and adults. You can see there were many more adults on board than there were children. Now, in terms of survival probabilities, if you look at either category, adult or children, and you look at the length of the bars, the length is proportional to the conditional probabilities of surviving given you're an adult or a child. Of the adults, you can see the great majority did not survive. At best, we have perhaps a third of the adults who survived. On the other hand, with respect to the children, it was about a 50-50 breakdown. About half the children went down with the ship, the other half were rescued. That's perhaps not as high as one would have wished it to be, but that also has to do with the fact that most of the children were in second and third class. If I go to the data input dialog box, I can change the factors. In fact, I'm going to ask for a tabulation of sex by survived instead of age by survived. And now you can see that the predominance of people on board were male. Perhaps at best a quarter of the folks on board were females. Of the females, however, a much larger percentage survived than of the males. If you were a male, your chance of survival was really fairly small. There, you can also change from sex to class. And now you can see that there's also a pretty strong relationship between class and the percentage who survived. Of those in first class, the survival percentage was relatively large. Quite a bit smaller for second class passengers and much smaller for both third class passengers and the crew. And again, you might remember if you saw the movie, they portrayed the fact that a lot of the second and third class passengers were locked on the lower decks for quite a long time and were not able to get into the lifeboats very quickly. Now, I can also use a handy function that's provided in Statgraphics called juxtapose. If I want to take two categories and form them into a single category. For example, I might go up here on the data input dialog box where it says row variable and type the word juxtapose. Juxtapose open parentheses age, comma, sex. What this will do is it will take age and sex, those two columns, and basically join them side by side. This will end up forming a single factor out of those two factors. It's easy to see when I press OK. I'll now have 4 rows of bars. I'll have one for adult females, a second for adult males, and then we have the female children and the male children down here. And you can see that the group with the highest survival percentage was the adult females, followed by the female children and then the male children, and quite a low percentage of the adult males actually survived. If I go back to data input, another juxtaposition that's interesting is class and age. If I ask for class and age, you can see 1, 2, 3, 4, 5, 6, 7 levels of class together with age. Now, there were no children in the crew, or there would have been 8 levels. You can see, though, if you look, take a close look at the children, for example, that if you were a first-class child or a second-class child, you were definitely rescued. All of those children were rescued. Of the third-class children, less than half were rescued, unfortunately. Now, if you're having trouble telling what color that first-class child bar is, if you go up to the analysis toolbar, you can expand the y-axis with this particular button here. And in fact, you can see that is a blue bar. All the first-class children did survive. It's a handy little feature. I don't know if you've all found it, but it's easy to scroll, expand, and contract along either of the axes. Okay, well, that's the Mosaic chart, and it's a chart that I often like to use to simply get an idea of the frequency distributions in my data. I now want to go and begin the discussion of a more mathematical procedure. In fact, a procedure called multiple correspondence analysis. A multiple correspondence analysis creates a map showing the associations amongst the categories of two or more categorical variables. It's used to help us understand relationships between categories of one variable and categories of another. To create a map that's interpretable in 2 dimensions, even though we may be working in more than 2 dimensions, an MCA starts by seeking a small number of dimensions that describe the greatest amount of variability amongst the categories. The variability amongst the categories typically being described as the inertia. Now, when I talk about variability, I'm really talking about how the distribution of the categories of one factor differs by levels of another. And as we'll see, it's something that can be measured through a chi-square statistic. The multiple correspondence analysis is very useful in demonstrating interrelationships amongst the variables. And it will give us some very interesting insights about who did survive the Titanic. Now, to do a multiple correspondence analysis, I'm going to move back to Statgraphics, and this time go to Describe Multivariate Methods. Here you'll see the multiple correspondence analysis. To run a multiple correspondence analysis, you can select 2 or more categorical factors. And I'm going to choose all 4 columns in this particular file. When I push OK, the Analysis Options dialog box will come up. And it'll give me a couple of options. First off, it'll ask me how many dimensions I'd like to extract. Similarly to a principal components analysis when I'm working with something like a correlation matrix. Since I'm going to display the data in 2 dimensions, I'm going to ask it, at least initially, to extract simply 2 dimensions. Okay? Often 2 dimensions can explain a lot of the variability. I also have a choice of how I want to base the analysis. Is it going to be based on an indicator matrix or a BERT matrix? The default is the BERT matrix. That's what I'll do, and I'll show you what that is in just a second. I'll then have a list of tables and graphs I can create. I'll add in the Mosaic Plot, take the other defaults, and that'll open up a multiple correspondence analysis window for me. Now, what I want to do is I want to explain what I can see if I do a multiple correspondence analysis. The first thing I can see is something called the BERT table. The BERT table will take each level of each of the factors and show how often they occur together, how often individuals are classified jointly one way and another. For example, this number here, 885, indicates that there were 885 adults in the crew. As I said, there were no children in the crew, so we get a 0 here. As far as first-class passengers, we had 319 adults, 6 crew. In second class, it was 261 adults and 24 crew. And in third class, it was 627 adults and 79 crew. Now, in looking at how one factor may depend upon another factor, it's useful, as I hinted a moment ago, to look at a decomposition of the chi-square statistic. The chi-square statistic is basically a measure of heterogeneity in the counts. How does the distribution of the categories of one factor differ by levels of another? It's an association between the two factors. What the program does is it first finds a dimension in the space of all those factors that explains the greatest amount of variability. And in this case, there's a single dimension, which I'll illustrate in a few moments, that explains about 45% of the variability, the heterogeneity amongst the counts. If I look at the first two dimensions, about 66% or about 2/3 of what's interesting essentially in this data can be explained by plotting with respect to the first two dimensions. Okay, we'll see this on the map in just a moment. Before I show you the map, however, I want to show you one other mosaic plot. As you can tell, I'm quite fond of mosaic plots. In this case, we actually have a matrix of mosaic plots. We have a mosaic plot for class by age, one for class by sex, one for class by survived. We have another for age by sex, age by survived, and finally sex by survived. There's a mosaic plot for every combination of the factors. And you can see some of the same things you were seeing when we did them two factors at a time. You can see, for example, class by age, there were no children in the crew, very few children in first class. Most of the children were in second or third class. You can also see, if you look at class by sex, that most of the crew were men, very few women on the crew. In first class, you had a pretty equal breakdown between men and women. Fewer women, though, percentage-wise, as you went to second class and third class. I'm going to be posting, incidentally, a PowerPoint presentation, probably sometime tomorrow, with the most interesting graphs and tables and so forth that I've shown during the webinar. So you'll be able to go to our website, for example, and take a close look at this mosaic plot. Now, on this particular plot, we see something called the eigenvalues. The eigenvalues, calculated from the BERT table, show me for each of the dimensions that I extract a measure of how much of the variability can be represented by that dimension. In this case, there are 1, 2 factors that appear to be statistically significant. Anything above this red line, this horizontal red line, is likely to be statistically significant. Anything below that is not. So in this particular case, the discrete plot definitely suggests that there are two significant factors, two significant dimensions that we should look at. The third is sort of borderline. Below that, the dimensions are not particularly significant. Okay, so 2 dimensions is a good place to be looking in this case. And now finally, I'm going to show you the correspondence map, which is what I was hoping to concentrate on when I did the MCA. Now, what you find on the correspondence map is a point for each category of each factor. Now, let me go to graphics options for a moment to points and make these a little bit larger so you can see the points a little more easily. There they are. I'll make them sort of big red boxes so you see where the points are. There they are. There is a point on this plot for every category of every factor. So there's a point for children and a point for adults, a point for males, a point for females. You see the crew, first class, second class, third class, and then survived versus not survived. What you're hoping to do when you look at a correspondence map like this is to identify significant factors in that data. What's causing these differences amongst the categories? Well, there are 2 primary dimensions. The X dimension here is pretty well defined by the difference between those people who did not survive and those people who did survive. Okay, here is a point for did not survive. Here is a point for survived. Where you lie along that first principal dimension is closely related to that survival probability. You can see over here where it says did not survive. The categories that are close to that are the crew, males, and adults. As you look over here at the point survived, the points that are close to that along the X dimension are first-class passengers, females, and also children. If you project child down to the first dimension, it's also very close to survived. Now, there's also a second dimension here. And the second dimension is pretty well dominated by child. Now, who's closest to child in the vertical dimension? Well, it's the third class passengers. Third class had more children than second class than first class. So the most interesting relationships in this particular data set really have to do with whether you survived or did not survive along the first dimension, and whether you were an adult or a child along the second dimension. And you can see by how close a particular category is to child or to survived, how related that particular category is to that other category. Categories close together on the map are strongly related. Well, it's an interesting map and allows you to look at multiple variables, multiple factors you can see in this case, just 2 dimensions. And I find it a very, very useful way for examining relationships. Okay. Now, the second procedure I wanted to look at primary procedure to look at today is the logistic regression procedure. The multiple correspondence analysis procedure is a good way to visualize relationships amongst the factors. But let's suppose we wanted to go in and actually build a predictive model. In particular, build a predictive model for whether or not a person survived. The logistic regression procedure is a very widely used procedure for doing that. And in particular, we're going to be talking about binary logistic regression. Binary logistic regression is designed to model variables with only two possible outcomes. And in this case, the outcomes are going to be survived or did not survive. Okay. Now, what it does, a logistic regression, is it builds a regression style model. A regression model to predict the probability of those outcomes. In this case, to predict the probability that an individual will have survived based upon various factors. And in fact, based upon one or more predictor variables. Now, when you build a logistic regression, the predictor variables may be either quantitative factors like sex, male and female, or, I'm sorry, that would be a categorical factor. They can be quantitative, such as age, if we know your age, or they can be categorical, such as sex, male versus female. Now, to understand the logistic regression, we need to start by talking about Bernoulli events. A Bernoulli event is an event in which two outcomes are possible. Okay, whether a person survived or not is a Bernoulli event. I'm going to let, for purposes of notation, the variable y sub I be equal to 1 if the ith individual in my data file survived and a 0 otherwise. The probability mass function for a Bernoulli event depends upon a particular parameter p. P, basically the probability of survival. And whether an individual survived or not can be thought of as p to the power y times 1 minus p to the power 1 minus y. Now, Bernoulli events, if I have independent events, typically build up and give me something like a binomial distribution. And when we talk about binomial distributions, we're typically talking about cases in which p, the probability of survival, for example, is a constant. I'm interested in a more complicated case, however. I want to let p, the probability that a person survives, be a function of various predictor variables. In fact, I want to build a function for p which makes the probability of survival a function of class, a function of age, and a function of sex. And actually build a mathematical model that lets me plug in your class, plug in your age, plug in your sex, and come up with a probability that you would have survived the sinking of the Titanic. Okay, now, in order to do that, we can't just do a simple multiple regression. Basic problem is that if I try to model the probability of survival using our multiple regression procedure, there'd be nothing keeping the model between 0 and 1, when in fact probabilities, of course, need to be between 0 and 1. Now, the most common solution to that problem is to use something called a logistic model. In a logistic model, you take P, divide by 1 minus P, calculate the log of that ratio, and represent the log of that ratio as a linear function of your x's. Now, what that gives you is a model for the log odds. P over 1 minus P is the odds you will have survived. Odds are defined by the probability of the event over 1 minus the probability of the event. Okay, so our log odds, when we do a logistic regression, are assumed to be a linear function of the x's. Okay, that's just enough theory. I hope to let you know what I'm about to do when I go to Statgraphics. So in fact, let's go back to Statgraphics and let's do a logistic regression. Okay, now I'm actually here going to use the other data set. The problem with this data set is that age is simply adult or child. I'm more interested in looking at the data set when I do the logistic regression using the file in which age is quantitative. So let me open up, if I can here, a data file called Titanic 3. This is the one I want to use for the logistic regression. Now, this file does not have the crew in it. It has only the passengers. It does, however, have the class of the passengers, whether or not they survived, their name, what sex they were, and what age they were. And you can notice now age is in years. It's not an indicator variable in this file. It's actually years. We also know the number of siblings on board, the number of parents on board, how much they paid for their ticket, and so forth. I'm not going to worry about those other columns, however. Now, to do a logistic regression, I'm going to go to Relate, Attribute Data, Logistic Regression. The dependent variable is going to be survived. Survived is still a 0-1 indicator variable for whether or not a person survived. Where it says quantitative factors, I'm going to put age. Where it says categorical factors, I'm going to put the class and the sex. Okay, so I'll have 3 predictor variables, 1 quantitative, 2 categorical. Okay. When I get to the analysis options dialog box, I'll have an option to fit, first off, either a first order model or a second order model. The first order model will look at each main effect. What class were you? What sex were you? What was your age? But won't consider any possible interactions amongst those factors. It's a little bit more interesting if I ask for a second order model, because that will estimate the interactions amongst the factors as well as the main effects. Over here where it says fit, I can have it fit all the variables, all the terms in the second order model, or I can do a stepwise regression like I can in multiple regression, in which case it'll pick out only significant terms. I'm going to go ahead and just fit all of them, however, so I'm going to say OK. As far as the tables and the graphs, I'll just go ahead. I'll take the defaults, except I'm going to ask for predictions instead of inverse predictions. Predictions is where I can go to actually make a prediction about whether an individual would have survived the Titanic or not. Okay. Now, when I press the OK button, it'll do the analysis and it will pop up for me some numerical summaries and some graphical summaries. Let's look at the numerical summaries first. In particular, the likelihood ratio tests. There's a section in the analysis summary which runs a test to tell me whether the different terms in my logistic regression are significant or not. There's a p-value in this table associated with age, another one with class, another one with sex. There's also one with age squared. Because age was a quantitative factor, I could go ahead if I wanted and fit a quadratic model rather than just a linear model with respect to age, which it did. There are also three terms for the interactions. There's an interaction between age and class, there's one between age and sex, and one between class and sex. Of those, the least significant interaction is the one where the p-value is shown in red. Okay, age squared has a p-value of 0.16, well above 0.05, also above 0.1. So it really looks like I don't need age squared. Now, if I want to get rid of age squared, I'll click my right mouse button. I'll go to Analysis Options. On the Analysis Options dialog box, there is a button labeled Exclude. If I push the Exclude button, I can then pick age squared, push the arrow here, and tell it to take age squared out of the model. A couple clicks with OK, and it will remove age squared from the model. And now I'll see that the p-values changed for all the other factors. Most of them are well below 0.05. The only one that's not is sex. It's at about 0.08. However, I'm certainly not going to take it out because there are several interactions involving sex, age by sex and class by sex, which are highly significant. Good rule, don't take out a main effect if you're going to leave higher order terms in the model involving that factor. So in fact, the only term I have decided to take out will be that age squared term. Okay, now, great, I've got a model. Now we need to look at it. A good place to go and look at it is the plot of the fitted model right here. What this plot shows me is on the y-axis, the probability, the predicted probability, estimated probability from the model, that an individual will have survived as a function of age. So the blue line here is the portion of the model that shows survival as a function of age for first-class females. Now, in order to plot this in 2 dimensions, I'm actually going to have to do several plots for you. This is a plot of survival probabilities for first-class females as a function of age. Actually, the blue line is the estimated model. We have 95% confidence limits above and below the fitted model. In the case of first-class women, the probability was well over 95% that they would survive, really regardless of their age. You can see there's not much regression with respect to age. Now, I'm going to take this graph, right-click, and tell it to copy this pane to the stat gallery. If you've never used the stat gallery, you should learn to use it. The stat gallery is a place where I can put several graphs side by side. And I'm going to go to the upper left-hand corner here, push the right mouse button and say paste, and have it paste that graph into the upper left corner of the stat gallery. Okay. Now, I'll go back to my logistic regression. I'll now press the right mouse button, go to Pane Options. Pane Options lets me change the levels of the factors at which I'm plotting this regression. So I'm actually going to change from female to male and press OK. Now you see a much different plot. If you're a first-class male, age makes a pretty big difference. If you're young, you have a relatively good chance of survival. If you're old, that probability of survival goes way down. Well, I'm going to right-click, copy pane to stat gallery, right-click, paste, and now you can see those two graphs side by side, the first-class females, the first-class males. Okay. Well, what else can we change? Well, we can change class. Let's go back to pane options, and instead of doing it for first-class individuals, do it for third-class males. Now you see a big drop in that probability, and in fact, I'm going to paste that one down here, and you can see a big difference between third-class males and first-class males. Same sort of a shape, but much lower. And then finally, let's go and do third-class females. Take that graph and paste it over here. Okay? And you can also see a much lower chance of surviving for third-class females versus first-class females. And also the effect of age is a little more significant on the third-class women than it was on the first-class women. Now that stat gallery is a very handy way of presenting a model that involves more than two factors, because you can see what happens, I think, quite clearly here as the other factors change. Okay, one more thing to do now, and that is to use the fitted logistic regression model. And I never really showed you the model. It's a little complicated. It looks like this. It has indicator variables for class and sex. It's got a ordinary regression term involving age. It's got cross products for interactions and so forth. Suppose I wanted to use this particular model to make a prediction for someone else. Now, there is no someone else in the case of the Titanic. But if you were a bank and you were modeling whether or not a person was likely to pay back their loan, you'd have a set of candidates that you fit your model on, and then a lot of individuals that you'd like to make predictions for. So just for fun, I'm going to go back to my data book over here. I'm going to scroll to the bottom of my file, and I'm going to put in a fictitious person. A fictitious person who's going to come back, and I'm going to put him on board the Titanic that night. Okay? Now, what I'm going to do is go down to where I have a free row in my file. Going to put in information about this particular person, all information except whether or not they survived. So let's suppose I had a person and this person was in first class. Okay, I'll go put a 1 there. Let's suppose his name was David. I must have had caps lock on here. There we go, David. He was a male, age 40. Okay. Now I don't need the other variables. They're not in the model. But here's another individual, an individual I'd like to make a prediction for. And I could put in a whole lot of individuals if I wanted to fill in more rows than that. But one's enough for you to see what's going on. A first-class passenger named David. He's a male, 40 years old. I'll go back to my logistic regression, and now I'll look at my table of predictions. And right down here, there will be a prediction for that row. We predict that the probability of survival for David is 0.35. There's about a 35% chance that a male in first class, aged 40, would have survived. Now, for those of you who are using version 17, I want to show you one other feature of Statgraphics you may not have found. Whenever you have a table like this, which has information for particular rows, you can right-click, go to Tabular Options. And on the Tabular Options pane, tell it you'd like to add another information or information from another column to the table. So I'm going to tell it add row labels based upon the column name. And then you'll see what it did is it added another column to my prediction table down here showing the name associated with row 1310, which was David. It's a handy feature of version 17 to let you get names rather than just numbers into tables like this. Anyway, about a 35% chance that David would have survived the sinking of the Titanic. All right, well, that's what I wanted to show you today. Let me go back for a moment to my PowerPoint slides. And I did put a slide into my presentation here on some recommended reading. There are two books that I find quite useful, quite good reading about what I've talked about. The first one is called Correspondence Analysis in Practice. It's from Michael Greenacre. It was published in 2007. The second is called Applied Logistic Regression by David Hosmer and Stanley Lemonshow. Okay, it's now in its third edition, 2013. So if you'd like to do some more reading, those are two pretty readable books, one on correspondence analysis and the second on logistic regression. The final thing I wanted to say is that we will be posting a recording of this webinar at our site, www.statgraphics.com. That'll probably be up sometime tomorrow. I'll also put up the sample data sets so you can play with them at your leisure. I found them on the internet, so they're publicly available. You can go ahead and try them. And I'll also put the PowerPoint slides up. Okay. I hope you found that useful. I tried to keep it under an hour today, which I also hope you find useful. I'm going to spend the next few minutes, though, looking at what questions you all may have sent to me. And let's see what I can do. The first question I was sent says, will this include data on the ship's crew? Well, one of my data files, I think, as you saw, the one I got from the Statistical Archives, the American Statistical Association site, had information on both passengers and crew. The second data file came from the University of Virginia, and that was more extensive information, but that was just the passengers. The reason I used two was age, though. One had age as a categorical, the other had age as quantitative. For the correspondence analysis, it's useful to have the factors as categorical. For the logistic regression, you get a little bit more information if you can handle something as quantitative. Someone else also asked, in particular, they were interested in the engineers aboard the ship. That I'm not sure about. Okay, I have listed in the PowerPoint slide, though, the URLs that you can go to that do have a lot more information about those particular data sets. So once we get these slides posted, go to the URLs that I've listed back near the start of the seminar. I think I listed the URLs for these particular data sets. Right, here's the first one for the first data set, and there's the second one for the second data set. They have a lot more information about exactly how the data were obtained and how they process the data and so forth. Okay. All right. Will a textual summary be available to participants? Okay, it says I'm involved in math education at the University of Alabama, and this would be great for educational use. Why don't you contact me if you would, and tell me exactly what would be helpful to go along with this, and then we'll see what we can do in terms of putting something together. Okay. Someone is having problems with the sound. I hope most of you can hear me. If you weren't able to hear me, there is, I think that this time it's probably at your end. I certainly hope so. Okay, another question. Is it possible to have survived as a supplementary variable, not participating in the map calculation and projected in the map built by the other variables? I certainly think it's possible to do that. I haven't tried that. That would definitely be something interesting to try. When you go into the logistic regression, there is an option to add supplementary variables. Where was I here? Oh wait, that was not the logistic regression, that was the correspondence analysis. I'm confusing myself. When you're in the correspondence analysis, you can use some variables to create the map and other variables to plot on the map, but actually they're not used to create the dimensions themselves. I'll have to look into that and see what you would get if you took survived out, just left age, gender, and sex, did a map of those variables, and did survived as supplementary. That could be interesting. I didn't try that. We can try that. Let's see what would happen if we tried that. If we put the Titanic data up here now, and I think the suggestion was to build the multiple correspondence analysis based on just class, age, and sex. Okay? And extract those dimensions so that you get a map involving just class, sex, and age. And then add the other variable as a supplemental row, or actually a supplemental column. I think there's a way to do that, and I don't remember quite at the moment. I'm going to have to look that up. Number of dimensions to... Oh, maybe it works like this. Maybe you put in class, age, sex, and then survived. Okay. Tell it, however, that the last one column is supplemental. Okay. What it would do then is it would build the map by extracting dimensions involving just age, class, and sex, but it would also plot on the map points for survived and did not survive. Okay, so I just did that. There's the survived. Again, it might be useful to increase the size of some of these points, make them a little more visible. I'm not sure which points are being used exactly, but we'll find out soon enough. Okay, well, in fact, let's make them even a little bigger. Okay, here is did not survive, right down here. Here is survived. Okay, did not survive is very close to male. Very close to crew. Again, you can see now it's actually sex that defines this first dimension. The strong definition of dimension 1 is now sex. Child, whether you're a child or not, definitely defines the second dimension. Yeah, it's a little bit in different interpretation because we have the characteristics of the people now defining the map, and then we're plotting additional points for survived or did not survive. Interesting. Thanks for the suggestion. Okay. All right. Does a logistic model handle missing values, or how does it handle missing values? You may have noticed when I fit that logistic model that there were in that second data file missing observations. Which one was it? It was Titanic 3. For example, for row 16 here, we don't know the age. What the logistic regression does is case-wise exclusion. It will throw out all rows that don't have complete information, don't have information on any of the variables. So if there are any missing values, that row is going to be thrown out. And that's the way it does it. Okay. Do you have intuition about when to use second order or look for certain items? Well, certainly the reason I fit a second order model to this particular data set was to estimate the interactions. I knew, for example, that your age might be more significant if you were in first class than if you were in third class. I also thought that age might be more significant for males than it was for females. In order to estimate interactions, which allow the effect of one factor to depend upon the level of a second factor, you've got to fit the second order model. So to me, it made sense to fit the second order model, check the p-values to see whether those interactions were significant, had certain interactions not been significant, then I could have removed those single terms from the model. But it would have been a very restrictive model to have used just a first-order model. It would have said that the effect of sex was the same for all classes and for all ages, and I'm not sure that would be true. A question not related to the present topic. What's more important, p-values or the overall percent correct in the prediction of the fitted model? Okay. You may have noticed in the logistic regression, and I guess I need to redo it here, that in addition to the p-values, there was a table that showed you how often or at least what percent of the passengers were correctly predicted by the model. So let me just redo this real quick, the logistic regression. It was survived versus class. Class was here, age was here, sex was here, I believe. Right. I told it to do a second order model. Oh, I also told it, I think, to exclude age squared. And then I told it I wanted predictions. Okay, in this particular pane right here, it actually tells you how many of the individuals would have been correctly predicted by my model. Now, what do I mean predicted? What the model actually gives you is a probability of survival. However, let's suppose I say if the predicted probability is less than 0.5, I'll predict that you don't survive. If it's greater than 0.5, I'll predict that you do survive. Okay? Make it a dichotomous prediction rather than the prediction of a probability. If I do that, I can look at this table of prediction performance. If I use 0.5 as a cutoff that will predict whether or not you survive or not, I would have been correct on 58.55% of the people that survived. I would have been correct on 93.86% of the people that did not survive, meaning I would have predicted correctly about 79.45% of all the people. Okay? Now, what's more important, how many people I would have correctly predicted or the p-values? That's an interesting question, isn't it? My general approach would be, let's build a statistical model with significant terms first. And then let's look at the performance of the model. I don't want to overfit the data. I don't want to leave a variable in the model just because it predicts my data a little bit better. Because I don't really want to predict my data. I want to predict new people that are going to come to me in the future. And I think the best approach is to build yourself a solid statistical model and then see how it performs. That was the approach I took, and that's the approach I think is useful. Another question not related to this webinar: will Statgraphics add definitive screening design sometime in the future? That sounds like an interesting idea. I'll look and see what we're doing for the next release and see what we can do about that. Okay, there's another question. What happens if the sample size will not run a logistic regression? Is there a sample size rule? I don't think there's a sample size rule. You certainly need data at all combinations of the factors. Now, I did at one point try to put in a data set that had class and children. But because there were, I'm sorry, I had crew and children. But because there were no children in the crew, it wouldn't fit a model that had an interaction of age and class. So if you're having problems fitting a regression, it's more likely that you have missing combinations of the categories. So it's having a problem estimating a potential interaction. From the results, can you summarize in one sentence, elevator speech, what kind of people were most likely to survive? The people that were most likely to survive were clearly first-class individuals, much higher probability than second, third, or the crew. First class, females, and children, although there weren't many children in first class. So I think you'll find the highest probabilities for the first class females. As you got older, as your class went down, it became more and more likely that you wouldn't survive. Okay, someone's asking us to add an ROC curve, which I think I do have actually, a prediction capability curve right here, sometimes called an ROC curve. That was beyond the scope of what I wanted to talk about today. You can see a discussion of that in the recommended reading that I gave. Okay, well, I thank you all for listening. That's the last question that I see on my list of questions. We will try to get this posted by tomorrow sometime. If you think it's useful for any of your other colleagues to take a look at, and also if you want to get those URLs and play with that Titanic data set yourself. Okay, well, that's it for today. We'll be back in about a month's time with another interesting data set to look at. Thanks a lot.